So we're going to take a look at some models and how we could represent them. So methane theoretically shouldn't be necessary, but if we were to build a tetrahedral molecule of methane, this is what we would be looking at. Okay, and so we can look at the varying different angles that it would look like if we try and look at the representations that are drawn up there. The hand-drawn one with the angle, or not hand-drawn, but the one with the angles on it would look something along these lines, where this bond and this bond are in the plane of the paper and therefore solid lines. This hydrogen, which is coming towards you, would then be wedged, which matches what's there, and then this hydrogen in the back is dashed going away, and that would then be our molecule. If we moved over one to look at that, what we'd be doing is doing a slight rotation to now saying that this bond and this bond are in the plane. Our hydrogen is coming at you on the left-hand side, dashed going away, which is again kind of hard to see there, but there it is. Okay, so they're all just different representations of that molecule. If you remember, there was one discussion that I talked about where you couldn't possibly have your two V's kind of overlap. So if we're looking at this, we have a V here, and then we have a V here that's in this plane, and then we have a V in this plane, right? And I said we couldn't do it where those V's overlapped, meaning if we turn the molecule like this, here's a V, and here's a V, okay? So there's that V, and then there's that V. You'd be like, well, but doesn't that show that crossing? But remember, the point of that V was that our solid lines can't all be in the same plane. And if we look at it in this case, yes, we do have those V's crossing, but we don't have any solid lines. There's no two bonds that are in the same plane as far as our paper, which is now vertical this way. These two in front would be coming towards you, which would be wedged. These two in back would be going away, which would be dashed. So that viewpoint never really aligns. This is why we should try and kind of lock down into that tetrahedral drawing. It makes it a little bit easier to deal with. Okay, we don't really get any kind of unique views behind these. We're really just kind of doing different rotations, and we can see slightly different versions. Okay, but what becomes important is when we say move to say ethane, which is 2 carbons and now the 6 hydrogens. So if we built out our model, we could then go through and draw what we saw. And what we would want to do is, again, include all the Vesper angles, our wedges and dashes and all that fun stuff to try and see what we could go ahead and do. And if we looked at this drawing, we're going to get something distinctly different than if we looked at it this way. And you might be, well, what did you do? Oh, I did a sigma bond rotation. We rotated about that sigma bond. Right? And you might say, well, I don't really notice anything obviously different about that. All you did was took this atom, which was in the same plane as this one, and we just did a rotation by 60 degrees. How does that change things? Well, for instance, that atom that was in the plane is no longer in the plane. It's in front, so it becomes wedged. This atom is now in the plane of the paper. Okay? And as far as our drawing goes, we might, again, really not notice much of a difference. Okay, come on. Sorry, we lost connectivity here. Let's try and bring it back in. But this is what we're referencing. So that first drawing, I'm pointing at the screen, not very useful. The one with the rotate. Notice where our hydrogens are. They're in the same plane, shown by the solid lines. So these 3 bonds are all in the same plane. And if we rotate that out, we're getting the drawing to the right, okay, to that far right up top, okay? Wedged, dashed, solid, okay? And that's the representation we're looking at, okay? We could shift down to the ones underneath that are trying to show that a little bit differently. And now the question comes is, how are they getting there? Okay, so let's go back, okay, and I'm going to attempt to point. I'm going to try something real quickly. Sometimes my device allows me to do this. Cool. Here we go. This guy right here, hopefully you can see that cursor, is this one. Those are the same representation, okay, exact same representation. Or same molecule. But what's happened is you took the molecule that was like this, and we're going to grab one of those carbons, and we're going to pull it towards you. Okay, so what you're looking at, let's see if I can, nope, that's the other way, is that. Okay, now what they're saying is we're going to take that front and we're going to rotate it. And now what we're looking at in my model is this guy. Okay, so all I did was take that hydrogen that was in the plane here and I rotated it 60 degrees. So now it's there. Okay, and again, we may not consider that that's that big of a deal. And it turns out that there is a pretty significant difference there, and it's something that we have to watch out for, okay? Because we might not consider it a big deal, when someone went through and was like, yeah, actually that is a big deal, they got to attach their name to it. And this viewpoint or shifting of our view, and now then the representation of how we draw that, gets named after the person that discovered it, and that's where we're getting what's known as the Newman projection, okay? I'll try and shrink that back down. So if we look at our Lewis drawings, pull out my little dealy bop, for our ethane, we could draw it out, hydrogen, hydrogen, whoops, that's not Lewis. I'm actually drawing the other one. I'm drawing the line angle. Our Lewis, carbon, carbon, right? So there's our Lewis. If we did a sigma bond rotation, we're not going to see anything significant. If we move to our line angle, we could say hydrogen, hydrogen, something along these lines. Okay, note again where our V's are, V, 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 back those out. And we will also find that we could have easily drawn it in a whole bunch of other variations as well, but these are the two kind of big representations like that. So there end up being two kind of ways that we could represent this. And again, we don't really see that big difference between those until we change our viewpoint. And that's when we shift it to on end. Okay, so we take that structure and we turn it and rotate it so that our viewpoint is coming at the end of it. So when we're looking at our Lewis structure, okay, there's our model again. This model is representing our leftmost structure up there. And now what I'm saying we want to do is look from this direction. Okay, so to do that, we're going to grab this carbon and we're going to pull it towards you as the observer. And now what we want to do is draw what we see. Okay, so ideally you're doing this at home with your own model kit, but I do have the model here, but we want to attempt to draw what you see. Okay, and if we were to go through and draw that, one of our kind of first attempts at drawing it might look something along these lines. Okay, where we've got our carbon, hydrogen, hydrogen, and hydrogen, and then that's it. Because we can't see the ones in back because they're hidden behind our initial system, right? If I did that, angled that perfectly, that makes it very difficult to see the atoms in back. Okay? So what we want to do is kind of change how we represent that drawing. And so this is where we kind of come up with a reverse perspective. Okay, so we'll call this our red, we'll call it blue. And what we're going to do is, again, pull that red carbon in front and reverse perspective. Things that are closer to you get bigger, so we'll make the thing closest to that eyeball, so that red thing, we'll make it really, really small. So reverse perspective. And then the blue carbon that's behind it, we'll make really, really big. Okay, ideally that would be a circle. And then we can draw on the atoms. And if we take a look at that red position, we have a hydrogen aimed straight up, and then we have hydrogens to the left and to the right. Okay, I don't want you to get too bogged down in saying the wedge is to the left and wedge is to the right. That all depends on the viewpoint. From this particular viewpoint, if we're looking at it from this end, this wedge is on the right-hand side, the dash is on the left. Okay? If we change our view and look from the other side, that could change. So don't just say wedge is right and dash is left. Okay? If we look at the blue one, we're going to have that hydrogen in behind, which makes it a little difficult. So we'll skew it just a little bit so that it stands out or so that we can see it. Okay? And that would be our representation. We could also go through and do it for the other one, and we'll do purple and green. In the case of the purple, again, closest to the eyeball, there's our dot. In this case, we didn't actually do a rotation of that, so we're still showing those hydrogens in that same configuration. The green one, the atom in back, is now the one that's different, because now the hydrogen that's in the plane, right, this was our plane of paper, is now aimed down relative to the eyeball. So here's our eyeball, that hydrogen is below the eyeball. So there's our hydrogen. We can draw on our other hydrogens, which would appear to be roughly 120 degrees away from each other. And so we now have these two drawings drawn in slightly different formats, okay, looking at them on end to visualize them. Does this shift in focus allow us to change our interpretation about these drawings? Are these equivalent? How can I say it without giving it away? I don't think I can. Are they equivalent in energy? Okay. Well, that first drawing, our red and blue one, you might say was kind of difficult to draw, okay, because of how those things overlapped. The other one was pretty easy to draw, okay, and it was easy to draw because they didn't overlap. Okay, so this was easy because no overlap. Okay, well, what was overlapping? Well, the bonds in the atoms. Well, what makes up a bond? Electrons. So if we're looking at the overlap one, we're overlapping electrons into the same space. Well, do electrons want to occupy the same space? No. Okay, so that overlap of electrons actually makes this a very high energy conformation. And in the other case, it becomes a low energy conformation because they aren't overlapping. They get as more space that they could potentially kind of float through. Okay? What does that mean for us? Well, then that means when we look at these line angle drawings, the case where our solids are on the same side versus our solids on opposite sides are going to be different energies. The solids where they're on the same side is going to be a high energy state, and when they're on opposite sides would be a low energy state. If we think back to how we draw butane, you would probably draw butane for carbons in the zigzag. If we did hexane, zigzag, right? And that's not hex. I think that one's hex. 2, 4, yeah, hex. We don't draw hexane in that kind of cyclic fashion. Note it's not cyclic because we didn't connect. Okay, well, why not? Look at how the groups are located. These groups are located on the same side. Okay, that same side was a high energy state. We don't want to do that. We want to stretch it out. So we've instinctively been drawing things in a low energy state, which is good. That's the point. Molecules will tend to achieve a lower energy state. Okay? These are sigma bonds. They can still freely rotate, but they're going to have a barrier to rotation through certain parts because we're going to go up in energy. Okay? This kind of realization is what's known as a Newman projection, okay, or viewpoint on it. And Newman projections really give us information about energy. So if at any point you're asked, what is the energy of something, you should probably be thinking along the lines of, dang, I need to draw a Newman projection. This Newman projection is a reverse perspective on our molecules, and it helps us to draw conclusions about how we perceive molecules. Okay? Because we now also have two distinct ways that we could draw them, we also have to come up with names for them. Okay? We could go back to the cis kind of trans because it's the hydrogens on the same side or hydrogens on the opposite side, but that doesn't quite work for us because which hydrogens are we talking about? Okay, well, we're talking about those two hydrogens being on the same side. Well, what about these ones? Or what about these ones? Aren't those on the same side? So cis and trans doesn't quite work for us. So instead, what we'll go through and do is note that these bonds kind of overlap, right? Kind of like how I don't know enough about astronomy, how we get eclipses, okay? Where the sun, earth, and the moon align in such a way that we start to lose visibility of certain aspects, okay? And that becomes the eclipsed conformation. In the other case, those positions are kind of alternated away from each other. They are staggered. Okay? And we have these two different energetics that we could now go through and determine. So when we go through and try and draw things, we want to draw things as much as possible towards the staggered conformation as opposed to the eclipsed. Okay? And that's what we're trying to work through. Kind of cool. Okay? We're going to skip propane because propane does the same thing. But if we move up to butane, we get more carbons. Okay? And those more carbons can potentially make this more challenging, because we could do a Newman projection down that red bond, down that blue bond, or down that purple bond. Okay? And I would recommend you go through and do it to see what you see. But what you'll find is that that red bond and the purple bond aren't really going to generate Newman projections that are really all that particularly interesting or different from what we've already seen. So those aren't going to be useful. Instead, we want to sight down that blue bond, and that would be down the 2,3 bond, hence the directions to look down that 2,3 bond. So what you should go through and do is build a butane molecule and then try and sight down that angle. Okay, and I was going to do that, but I don't have enough carbons in front of me. Sight down that bond and draw out the potential ways that you could then rotate around that 2,3 bond. How does that align the individual groups? And what you'll end up seeing is that there are differences in how you would draw it. Those differences come out largely with eclipsing. Okay, so we'll still get the eclipsing. We'll get varying levels of eclipsing, but then we'll also get varying levels of staggereds. We can get it where our CH3s are on opposite sides or are kind of close to each other. When we look at the eclipsing interaction, we'll see something similar. We can get the eclipsing interaction where it's a CH3 and an H on our back carbon, or we could get the eclipsing interaction where it's a CH3 and a CH3 butting up in the back. Whoops. So we get some new kind of interactions that come out of it. The eclipsing interactions are all exceptionally high in energy. Okay, and if we consider them in this rotation, those end up being at energy maximums. Okay, because they're at energy maximums, they can't exist. Think back to your energy diagrams that you saw in 152 or second semester general chemistry. Those were transition states. That's how we were transitioning from one point to another. They don't actually exist. It's just a shifting. Okay, and for that reason, I would argue that we don't need to stress about differentiating those. We need to acknowledge that they're different in energy, but we don't need to really name them. Okay, so our eclipsing will still just get called eclipsed. These staggered, however, are energy minimums. Okay, and as an energy minimum, they do exist. Because they now exist, we do need to actually differentiate these. Okay, are those different in energy? Okay, well, in that first case, what do we have? We have the methyls close to each other. Okay, in the second case, we have those methyls as far away or as opposite as possible. I'm just going to say that spelled right. Okay, so we do come up with names for these. Okay, and it's a bit odd, but we're just going to run with it because it helps to remember how we get those relationships. You may not be male, but you may have heard something about bathroom etiquette as far as urinals for males go. Right? So when men go to the urinal, you usually have 3 or 4 banks or places that you could go through and P. So when you're the first person in, it doesn't matter. You can really have your own pick. So we could put our first person in here. Okay. The next person that comes in needs to go in over here. Okay. Consider it kind of a privacy thing. You're getting as far away from that other person as possible. Okay. So that large distance away is the equivalent of our fully opposite. This is what is known as our anti-conformation. Okay, as far away as possible. What is not allowed, okay, so let's get rid of that second person. We're not necessarily not allowed, but kind of frowned upon, is if we went in and as that second person, we started peeing right next to the first one. That's kind of awkward. You're like, why? You have all these other places that you can pee. Why are you peeing next to me? That's kind of awkward. Well, the French word for awkward, gauche. Right? So those two methyl groups now really close to each other is that's a bit gauche. Like that's stepping on some, societal norms. We don't really want to do that. Okay? So we get our anti and our gauche. And just for giggles, because we can, the absolute worst place to come in as part of the Guy code, and I've never heard anybody doing this, is you walk in as the second person. You're like, well, dang, I want some company. You don't pee in the same urinal, okay? That would be an eclipsing interaction. And that eclipsing interaction generally creates a much higher energy state, and it could potentially cause fights. So that's why we separate out, okay? So we get the eclipsing, peeing in the same urinal, or a bit gauche, peeing too close to me, okay, at the urinals, or anti, I have my own personal sphere of happiness, of pee happiness. Because you're really far away from me when you're going to pee. Okay? Those people being like, this is ludicrous and that's not true, talk to any guy you want to, you'll probably get the same story. Okay? So that's what we're dealing with. Newman projections are really just man code pee etiquette. I can't believe I just said that, but whatever. Okay? So what this can be done or how this could be organized is go through and quantify this. So if we were to go through and look at labeling these things, this is eclipsed, okay? And those two methyls are very close. So this is eclipsed high. We then move to a gauche, which is a staggered, okay, low. We then move again to an eclipsed, but not as high. Okay, because we're having the hydrogens overlap with the methyls, not the methyls overlap with the methyls. Then we have the kind of staggered again, where those are super far away from each other. So this is very low. And then we repeat, we repeat, we repeat. And what does this turn into as far as a diagram? Okay, well, we start at a high point, a very high, because those dudes are peeing in the same urinal. We then get a low, because, they're standing kind of next to each other. Maybe this is peeing directly behind the guy versus peeing next to the guy. Okay, so it's high in energy, but it's not quite as high. Note there's a gap there. Then we get this really low. Then we go back, and then we go high again. Okay. That's all we're trying to do is draw this out. The next part to realize is that all we've shown is 0, 60, 120, 180. What's happening is to go from 0 to 60, you have to rotate. As you rotate, you're going to slowly become closer and closer. And then you'll rotate and get higher, and then lower, higher. Whoops, I missed that low. Low, high. And that's what we're talking about here. We're looking at how we can transition through these. These peaks, when I was talking about peaks, those transitions are our eclipsed conformations, okay? Different levels of eclipsed. These minimums, okay, in blue are our staggered conformations. And because they now exist, because they're a minimum, that's why we bring in the name of gauche and anti to describe those. So you could be asked, say, given, starting with this molecule, that gauche, show what an energy diagram would look like. Okay, so now when you do the rotation, you're starting your diagram here, and you're continuing out your rotations all the way down. So all the way down. I did a horrible job on that. Okay, this is why drawing in those energy minimums and maximums would help. Okay, so you're just shifting where your focus is within this. The absolute energy values within this I don't care about, so don't stress about those. Okay, we could go through and look at those. Our textbooks will show that, and you could talk about the exact specifics of how much steric hindrance and energetics go into it if you change the methyl to an ethyl versus an isopropyl. And it's just not necessary for our discussion. So don't worry about that. But the relative amounts are very important, and you should be aware of those. Okay? This will then push into our cycloalkanes, because now we've got this idea of what happens with chains. Well, what happens with rings? So you should be able to go through and note hybridizations behind each of these carbons, and you'll note they're all sp3 hybridized because they're all single bonds, which means we should be getting 109.5. And if you look at bond angles and do your geometry and trigonometry stuff, you'll note that we don't get that 109.5, which then means we create a strain within the molecule. Okay, that strain, okay, is an angle strain, which becomes most apparent with the cyclopropane, because that is now forced in at a 60-degree angle. That creates a lot of stress within the molecule, and it does want to pop open. Okay, if we move through to the bute, we're looking at a 90-degree. Okay, and then I'm not good with trigonometry after that, and another issue pops up, which we'll address in a second as well. Okay, so we're concerned about those angle strains addressing this. The other thing that we should consider would be our Newman projections, because the whole point of Newman was to see the alignment of those groups and how they could potentially cause energetic issues. To do that, you really have to be able to build the model for each of these. And that's where things are going to become a bit dicey to go through and do. And that's that popping sound you're hearing because I'm attempting to build it while you're not looking. And what we would do is try and go through and see what happens in each of those cases. Okay, so I need just a little bit more here. Sorry for the little bouncing sound. Ow, God, I really hate this kit. And our last one for the butane. And so what we will go through and do is attempt first, let's get rid of this, and look at the prop. So there's our 3 carbons. I will throw on, this is the improper bond for this, but we're going to do it anyway. Okay, and we want to make this a prop. So to make this a cycloprop, we need to connect this. Okay, and you'll note that that doesn't connect very easily. And in fact, if I manage to pull it off, which sometimes I can, nope, can't pull it off. Okay, so we'll just kind of hold it there for the moment. Okay, if we got that connected, you would note that there's a lot of strain behind it. Okay, so that's an angle strain. We could also look at kind of a bond overlap strain that would be addressed from our Newman projections. If we look at the Newman projection on that ring, note that our structure is also eclipsed. Okay, so we get lots of these energetic things that pop in and make this molecule very, very stressed. Okay, it becomes a little bit easier for me to draw, or at least build, if we move to a cyclobutane. Okay, so there's the butane, and if you look really closely, you can see that there's some spacing kind of popping out on those, and that spacing is because it really doesn't like this. It's a pretty stressed molecule. And if we turn it on end, okay, we again look down that side and we see that those bonds eclipse each other. Okay, that eclipsing makes it unstable, and one of the things that the butane will do is it'll start to spin just a little bit. Okay, and as it spins just a hair, these start to fall out of being in the same plane and will become like a pseudo uneclipsed. Okay, and that's one of those kind of interactions. Our molecule tries to minimize that issue. Well, what happens if we add yet another carbon, okay? And we move up to the pentane, okay? And you might notice that it gets a little bit easier to build. And one of the things that if we try and actually push it together, you'll note that if we just kind of flex it a little bit, we'll note that it actually flexes a little bit better where they aren't all in the same plane. So we're looking at it from the side, our carbons aren't all in the same plane. One of them pops out a little bit, okay? Why does it pop out and make that happier? If you do so, what happens on that Newman projection? Note, those aren't fully eclipsed. If we bring it flat down, they'd be fully eclipsed. That's highly stressed. But because the ring has now opened up enough, we can actually start to approximate our 109.5 degrees of our tetrahedral structure. That causes a slight puckering of the molecule, which actually stabilizes our Newman projection with those bonds kind of overlapping. This happens even further when we move into the cyclohexanes, okay? And the cyclohexane becomes the epitome of stability because it pretty much guarantees that each of our carbons gets locked into this 109.5. As we go up to heptane, it actually goes up in energy again because we now have too much motion and too many different things can happen, and it starts to limit the ability of the molecule, which means our cyclohexane becomes the optimal structure to study, and we'll see that in our next video when we're talking about cyclohexanes and ultimately how to draw them. Okay, and with that, hopefully you've got a better understanding of what's going on with our models. The next video is strictly a model video, so go through and watch that and pull out your model kit and start playing around with these because it's going to help you better understand how to manipulate them. Have a good day.